Let's start second part of electrochemistry from Ostwald's dilution law. According to Arrhenius' theory of ionization, when an electrolyte is dissolved in water, there is an equilibrium between the ions and undissociated molecule. For example, for a binary electrolyte AB, we have Ostwald in 1888 pointed out that the law of chemical equilibrium can be applied to this ionic equilibrium. As a result, he obtained an important relationship known as Ostwald's dilution law. Suppose the initial concentration of the binary electrolyte AB in the solution is C moles per liter and alpha is the degree of dissociation, then we will have AB gives A positive plus B negative. Initial concentration C moles per liter 0 concentration at equilibrium C minus C alpha gives C alpha is equals to C into 1 minus alpha. Applying the law of chemical equilibrium, K is equals to C alpha square upon 1 minus alpha. The equilibrium constant K for the equilibrium AB in equilibrium with A positive plus B negative is called the dissociation constant or ionization constant of the electrolyte AB and may be represented by Kd or Ki. Like any other equilibrium constant, Kd is constant only at constant temperature. The units of Kd will be same as those of concentration C. If degree of dissociation alpha is very small, as is actually the case of weak electrolytes at ordinary conditions, alpha can be neglected in comparison to 1 in the denominator of expression 1. Then the approximate formula becomes Kd is equals to C alpha square or alpha square is equals to Kd by C or alpha is equals to Kd by C under the root. Equation 1 and 2 are two expressions of Ostwald's dilution law. Expression 2 can be expressed in words as follows. For a weak binary electrolyte with a small degree of dissociation, the degree of dissociation is inversely proportional to the square root of the initial molar concentration. Further, SC is the concentration in moles per liter. Therefore, the volume V of the solution containing 1 mole of the electrolyte will be 1 by C liters. Putting 1 by C equal to V, the expression 1 and 2 can also be written as Kd is equals to alpha square upon 1 minus alpha V and alpha is equals to Kd V under the root, where V is the volume of the solution in liters containing 1 mole of the solute. Thus, Ostwald dilution law may also be defined as follows. For a weak binary electrolyte with a small degree of dissociation, the degree of dissociation is directly proportional to the square root of volume in liters containing 1 mole of electrolyte. Validity of Ostwald dilution law. To test the validity of Ostwald dilution law, that is to verify the law experimentally, the degree of dissociation alpha was determined from conductance measurement using the formula alpha is equals to lambda C by lambda naught at different concentration for a number of electrolytes. For each electrolytes, the data were fitted in equation 1 to see whether the value of Kd comes out to be constant or not. It was observed that number 1, the value of Kd comes out to be constant only for weak electrolytes and that too when the concentration of the solution is not too high. That is for the dilute solutions only. Number 2, the value of Kd does not come out to be constant for strong electrolytes. Thus, it may be concluded that Ostwald dilution law is valid only for weak electrolytes in dilute solution. That is why it is called dilution law and it does not hold good for strong electrolytes. As an example, the results of a weak electrolytes, namely CS3COOH, and those of a strong electrolyte, namely KCl, are given in table 2.2 below. Importance of Ostwald's dilution law. Ostwald's dilution law is applicable to weak electrolytes only. As such, it is very useful in the calculation of the dissociation constant Kd of the weak acids and weak bases by determining the degree of dissociation and from conductance measurement delta C by delta lambda C by lambda naught at any concentration C. Having determined the value of Kd, which is the constant for a particular weak acid or weak base at a particular temperature, and the degree of dissociation alpha of that weak acid or weak base can be calculated at any concentration. Thank you.